All right, welcome to an introduction to kinematics and dynamics and ether cosmology presentation. We're going to be adding some clarity to the debate that took place last night between Whitsitt and Darrell on modern day debates. At around roughly an hour into the debate, Darrell makes the comment that he can derive G from big G, just so he gets through the derivation here, canceling out the masses and showing the kinematic derivation of downward acceleration just based off of G, right, with no dynamic cause, which was the point that Whitsitt was making, was that when you apply these equations to the sky, the mass cancels out, which makes them kinematic equations and not dynamics. And we'll get into the distinction of what all of that means here in a second to add some clarity. All right, so before we begin, all of this entire presentation will be available, link in the description, on my Obsidian publication. And then any of the references that you may need, you can head over to get.ethercosmology.com and click on, the link will be in the description too. You can follow this link, and then any of these sources in here that you see that you might want, you can go, oh, Shakar, what's that? How do I get his book? Oh, you just start typing in Shankar, and his book will come up. Anything in the title or the author, it should come up. My Zotero automatically renames PDFs to the author at least. So as long as you know the author name, so Einstein, you should be able to get anything that has or starts with Einstein in it. Anyway, all resources are available there if you need any citations or help with research or anything. So anyway, let's get back to the issue at hand here. So Darrell derives G kinematically, and that's Whitsitt's entire point, is that it's not a dynamic cause, it's a description of the effect, right? The acceleration. So that's all that was being put forward there. And then Whitsitt would reiterate that, and then Darrell would rederive it, right? Which seems confusing because it seems like, well, Darrell must be doing something dynamically, right? But the distinction here was lost on him, and he wasn't. And then obviously, you're in a debate, so you're not going to concede to that immediately, right? Because it would defeat his entire premise, right? So we'll move on from that now, and then we'll get into the specifics of kinematics and dynamics, and then you, the viewer, can decide for yourself. And then obviously all the sources are provided too. Maybe you disagree with me, maybe I'm wrong. You're free to look over the sources and draw your own interpretation. All right, so introduction to kinematics and dynamics. Here we go. So starting off with Robert Shankar's book on fundamental physics of mechanics, relativity, and thermodynamics. He lays out the preface for what kinematics and dynamics are and the distinction between the two. So in the Newtonian procedure for predicting the future, the given present has two parts, kinematics and dynamics. Kinematics is a complete description of the present. It's a list of what you know about the system right now. For example, if you're talking about a piece of chalk, you will want to know where the chalk is and how fast it's moving. Dynamics then tells you why the chalk is moving, or why it moves up or down, so on and so forth. It comes down due to the force of gravity. In kinematics, you don't ask the reason behind anything. You simply want to describe things the way they are. And then dynamics can tell you why the description changes with time, or why that description changes with time. Okay. So the big distinction here would be mass is supposed to be the dynamic cause of the acceleration, right? But you don't need mass or big G to derive G, right? You can do it kinematically based off of how high something is and how long it takes it to fall. So so G, right, then becomes just A, it's acceleration, right? Some sort of downward acceleration. You can represent that entirely for what it is with kinematics without introducing any causal mechanism or even trying to derive it from a causal mechanism, right? Which we'll get to here in a minute. Here we have the equations that govern kinematics. You'll notice that none of these equations account for any sort of dynamic cause. Like there's no mass, there's no friction, nothing, right? This is all velocity, acceleration, and time. And what you could do with these is you could take derivatives of time, etc., or from the acceleration, and you can figure out how much constant velocity there was, or how much change in position there was, or how much change in position there will be based off of the velocity, constant acceleration, or constant velocity or constant acceleration, etc., right? You can figure out all of these terms and the positions of objects based off of their trajectory. right, using these equations with no regard for causal mechanisms. And for clarity and dimensional consistency, there's a visual bug in Obsidian, and this equation 3 is supposed to end in a t squared, but it looks like a regular t, but it's t squared. All right, so we'll move on now from that. Okay, so like in regards to dropping an object, but let's say you throw an object, right? So kinematically, let's say I'm throwing an object to you, right? Throwing a baseball at you. Your brain immediately is tracking that baseball and you're predicting where that baseball is going to go. That's all kinematics. You have a velocity and you're estimating where its trajectory is going to be over time based off of that velocity. Right? You're not like, oh, he threw it this hard, the baseball weighs this much, the person throwing it applied this much force to it due to the forces due to gravity and air resistance. It's going to cause this much friction on the ball, therefore it's going to lose this much. No, none of that. It's not what's happening, right? Kinematics is just the velocity at that time, right? And predictions based off of that. So that's a really easy way to look at the distinction there. And then the dynamics would be when you're introducing the friction, the forces, the mass, trying to figure out how far the ball could be thrown, how much impact it could have, et cetera, based off of those factors, right? So different equations will tell you different things about the motion, right? Or different things. Dynamics and kinematics will tell you distinctly different things about the system that they're analyzing. All right, so introduction to the principles of dynamics. The principles of dynamics is a subset of mechanics that deals with bodies under the motion of forces, or bodies in motion under the action of forces. The subject of dynamics is completely captured by Newton's second law. The summation of force is equal to F equals ma. Yeah, so as I said equals twice there, but anyway, to study dynamics, we must be able to handle the correct force analysis. So that's where you would get into figuring out, okay, do I need to apply friction? Do I need to apply air resistance? Do I need to apply, et cetera, to figure out what forces are necessary in the system that you're analyzing to provide accurate descriptions? Because maybe one force or something will cancel out, so you won't have to account for it. Maybe it'll be a negligible thing and it won't be a factor in your analysis, right? So by doing by handling the correct force analysis and figuring out all that, that's going to give you the most accurate predictions for the motion using actual dynamics being the causal mechanism and the forces at play in the system when the prediction, where the motion is occurring, right? And then to kind of reiterate on that, we start getting into a system of particles that there's forces being acted on them, and then they're going to predict the motion of the particles based off of those forces, right? So these are distinctly different concepts in physics and mathematics, right? Okay, so a big argument that was put forward from Daryl was that big G is proves the through orbital mechanics proves the mass of the objects, proves that dynamic cause, right? So when you're applying orbital mechanics and you're using what's the equation? I can't remember off the top of my head. It is, show me on that. It needs to go over here. So it's Fg equals gm over 4 pi squared. So what you would do with that, right? You would cancel out the masses, and then it would just be based on a ratio of the constants being in relation to the periodicity, right? So we'll come back to this in a second. But when you're using this big G and these m's, people are like, oh, we're doing dynamics, right? Because Kepler's laws are all kinematics. Kinematics, right? People would watch the stars, they would watch the planets, they would watch them complete circuits. So you would take an observation at one day of the year, or at a specific time of the year, and then you would wait until that planet or star or what have you has completed a circuit and come back to that original spot. That would give you the periodicity. So when you start applying these equations with periodicity and the mass canceling out, it becomes a ratio of the constants and the periodicity. And by canceling out that dynamic cause, you can't say that it's due to mass attracting mass in the way that you would, conceptualize it for the validity of the heliocentric model. So here. So now we'll come back to Kepler's laws. Okay, so Kepler's first law is that the planets, or the orbit of the planets, is that of an ellipse with one of two foci points being the sun. So what that means, if you take an ellipse, there will be two foci points, right? This represents an equidistant, what was it? Line from the center there. Anyway, what this represents here is that a planet will be, when it's closest to the second foci point of the ellipse, that's when it's aphelion, that's when it's furthest away. And then when it's closest to the sun, or, its orbiting body, that's when it's perihelion. So they describe the periodicity as, it's creating an ellipse. It just deviates from a perfect circle and it's an ellipse, right? So that's how they work out the geometry of the ellipse in relation to Kepler's laws. Right, so now we have Kepler's second law. The planet in its orbit sweeps out within equal areas and times. The planet moves faster when it's perihelion and slower when it's aphelion. Okay, so now the second law is going to tell us about the speed in which things move in the sky in relation to where they're at on their elliptical orbit. Okay, cool. So far, still kinematics, okay? All right, so to give another representation of that, aphelion and perihelion, slower, faster. So faster as you're coming into the sun, then you start going slower, faster, slower, right? So that's how they've defined the orbital geometry. And then Kepler's third law is that the square of the orbital periods of the planets are directly proportional to the cube of the semi-major axis of their orbits. So what that means is that when you take the periodicity of the event and you relate that to pi, right? Because what they've done, right? They have the periodicity. They don't know how fast it's moving, but they have how fast it's going to complete a circle, right? So you turn, You turn velocity into pi to complete a circle, to complete a circuit, and then within that ratio, that will give you the semi-major axis of it. So when we get to the semi-major axis, when we're looking at the orbital geometry, right? So based on how fast this planet completes an orbit, that periodicity is proportional to the cube of the semi-major axis. So this is how they establish distance in the sky using pi and the periodicity of an event. So this becomes a constant, right? This becomes the length of the planet in relation to the sun, right? All right, so now moving on to big G and M, right? Because we've got these constants. We've got a big G and we've got an M. So they're putting forward some evidence for dynamics, and it's like, okay, let's take a look at what would happen here. How'd they establish G and M of the Earth, right? So they took two spheres, hung them on a torsion beam, and measured the torque angle of the wire in relation to the two spheres, right? So again, here they establish the constancy of the torque of the wire by applying the periodicity. So when the balls are moving back and forth, they establish a periodicity for that, which is known as, let's see, what did they derive that under? K theta. Yeah, so K would be the constant of the wire, and then like the constant torsion of the wire, and then the theta would be the deviation due to the gravitational attraction, right? Due to this mass attracting mass situation, right? So when you go to figure all this out, the force between the two masses in relation to the torque is F times D, where D is the distance between the masses and the force would be the force, and then T would be the torque, right? So all they're doing is using that angle and saying that this is produced in relation to big G. So here, taking the measurements from Cavendish, you would go big G equals the mass of the one sphere times the mass of the other sphere times the torque over R squared. And that's going to give you that theta angle, right? That's going to give you the big G there, right? So that's how they derived it. So M, mass, right? They're using downward acceleration. They're using the weight. They're using G, little g, to derive big G, right? So all they've done here is they've hung two spheres that are under downward acceleration, right? But it's canceled out by the thing, by the torsion beam and the wire, right? And they're just oscillating back and forth. And they're like, okay, well, based on this angle here, that would be caused by that gravitational force between these two masses, right? And so what they did is they're in their way of thinking is that they've zeroed out G, and the force that the attractive force they're looking at between them is big G. And then from that, they can backwards derive what the mass of the Earth would be to produce that effect, right? So once you have the mass of the Earth, right, from Cavendish, you got your mass of the Earth and you got your big G now. So now you can go, okay, how long does it take for the sun to complete its analemma, right? So 360 days thereabouts. But when you apply that same relationship, this GG, when you go to solve when you go to solve GMM over R, right, you get this. Or well, you get an equation that could backwards cancel out to give you what the mass of the sun would be to produce the orbit in relation to this in relation to the Earth's mass. So it's like, okay, now we've got the mass of the sun somehow, or not somehow, but algebraically we've worked out what the mass of the sun would be. So now they take each system, they go, okay, Mercury is going to do its orbit. Oh, look, the periodicity of its orbit tells us how far away it is now. Right? And then when they start swapping in G and M as the causal mechanisms, they think that they're deriving the physical distance based on the mass equals mass relationship, right? And because this is all based off of proportional ratios and constants, where the mass, where one of the dynamic causes cancels out, you don't actually know if this is correct. This is just ratios of constants and periodicity. It's the same thing that Kepler did, but because mass attracting mass is now associated with Cavendish, people are like, oh, snap. This is why the heavenly bodies move. Mass attracting mass is the dynamic reason why these bodies move now. Okay. So we're going to move on to the next portion now. So that was, we already covered the torque and Cavendish. So that was basically lining up all of that to explain how they got G and M to even start applying to the periodicity of the sky, to start backwards deriving mass for everything so that they could be like, oh my God, look, how does it fit? Well, it's just ratios of what it would have to be in regards to the constants and the periodicity. So these values, these starting values, G and M, whatever they lock themselves into, right? They could be any value, because when you're doing physics, you need constants. You do need to establish baseline constants and whatnot. Now, do these constants have physical meaning, right? This is where we're going to get into that implication. But needless to say, with this measurement that they've narrowed it down to, it could have been anything. You could do charge potential, like you can make it anything, right? But anyway, these constants are established and then applied to the sky. And from there, that's how the narrative goes. That this is mass attracting mass, this is actual dynamics. Okay. So, oops. All right. So just a quick reiteration here. These are Kepler's laws, and we already went over the laws there. The ellipses, the speed when they're aphelion and perihelion, and the square of their periods is proportional to the cube of their semi-major axis, which gives them their distance in relation to the sun. So when they use that with the Earth, that's how they came up with the astronomical unit for 93 million miles. Right? So then everything after that is like, oh, it's all in astronomical units, right? How far away is this planet? Oh, it's, X, Y, Z astronomical units. Well, how does that work? Well, it comes from that exact ratio. So these are Kepler's laws. The first two were published in 1906 and the third in 1619, sorry. Thus, they precede Newton's laws of motion by nearly 70 years. As a matter of fact, Newton deduced the laws of gravitation from Kepler's laws and his own laws of motion. All right. So when we get into that backwards compatibility, you can derive one from the other, right? That's what we're told. You can derive one from the other. But when you do that, you realize it's just based off of the constancies as a ratio to the periodicity. Now, what happens when you add the mass back in, you might ask? If you add the mass back in, this changes the orbital path by 0.1%. So if you were to take the system of the sun and Jupiter, right, where the mass cancels out in one of these, right, if you GM it, one of those M's cancels out. But if you put that M back in, right? You get a change of 0.01 or 0.1%. So nothing. It's not relevant at all. It's not. And this is like the biggest example that they give, right? So Jupiter and the sun, right? Now, if you do Earth and a satellite, same situation. So real quick on satellites, anything in the sky, these equations apply to Kepler's laws and how they do this with the periodicity. So let's say you have a satellite going overhead that you see like, oh, a GPS satellite, right? Well, you don't know how high it is. You don't know how fast it's moving, etc., right? But what you do know is the periodicity of it. And from that, you can backwards derive what the altitude would be based on that. And then from that, you'll have how fast it would have to be to clear the sky for you to meet that periodicity, right? So it'll reify that orbital altitude for you based off of the speed, because if it's at that altitude, it has to be traveling at XYZ speed to complete its periodicity, right? But if you don't know, if you don't know the altitude and you're just going off periodicity, could be any distance away from you, right? So if a GPS satellite is sending you signals that are offset to correct for, let's say, I don't know, the Sagnac effect, and meridian corrections are already baked into the clocks as they're passing over GPS stations on the ground. So they're constantly correcting to the coordinate system and you're already getting offset coordinates sent to you. Well, you're not going to know anything about the actual altitude or anything like that, because all of that is going to be sent in with the coordinates, right? And you'll just be looking at the periodicity of the satellite and you'll be looking at the object in the sky and you'll be assuming, oh, it must be 20,000, what was it? What is there? 20,000 kilometers in the sky traveling at 17,000 miles an hour, I think it is, or 12,000. I can't remember the velocity for GPS satellites, but it's somewhere in there. Anyway, they must be traveling this fast. Otherwise it couldn't complete the periodicity at that thing. But all that information, right, is already cooked into the signals that you're getting. So just based off of observation alone, you don't know how high the satellite is. You can only make that approximation based off of a ratio of constants that are given to you, and then assuming that they're correct. And assuming that those are correct, right? Because a satellite, let's see, for the example, right? Let's forget about the satellite for a quick second. Let's take it back to the sun and Saturn, for example, right? Let's take it back to the solar system. So the sun, they say, is 800 million miles away based off of these ratios. Well, if G and M were wrong, right, they would still work out proportional with Kepler's laws, because Kepler's laws are periodicity based off of the ratio. So if they ever needed to adjust anything by 600 million miles or 200 million, everything in this entire system would scale invariantly, it would scale covariantly. And that would adjust all the distances of all the objects proportionally. And you would never know the distance of any change. It would still be completing the periodicity above you at the same speed. You would never know. Right, so that's the huge distinction here to be made. Sorry, I was looking at the time here to see where we're at. All right, so as far as dynamics goes, we've still only have observations and equations where the dynamic cause canceled out. So what do we do here? What do we do? Well, now we move on to experiment. How do we substantiate the causal mechanism? Because if the Earth, for example, right, has a mass of whatever it is of that big M and that G relationship with the sun and its mass, right, that produces a velocity of 30 kilometers a second. And that will allow the Earth to complete its periodicity, its 365-day orbit around the sun, to give you that cube of to give you that proportionality ratio of the cube of the semi-major axis being proportional to the cube of the periodicity. So now we're going to get into some tests to substantiate that velocity. Okay, so if their Earth is moving that fast, there's going to be some effects that are going to be mutually exclusive, right? So in the 1800s, Arago first proposed that he should have to adjust the focal length of his telescope to see every 6 months when we're moving towards the stars or away from them. right? And what he found was he didn't have to adjust it at all. So that sucks for them. So he's like, okay, well, maybe that's just like whatever. Maybe we could try a different one. Let me half color my telescope with a crystal prism. And when the starlight intersects with the crystal prism, it'll be slowed down due to the refractive index of the crystal prism. And I'll have to tilt my telescope a little further to compensate for that correction, because the Earth's velocity, you're essentially going to be moving from underneath that starlight as it's being slowed down as it's traversing through that crystal prism. Well, and this is to give a example of what it would look like, when you put a stick in air, stick in water, and you see that displacement. Oh, okay, so it's gonna change it a little bit. Okay, so what happened? So as E.T. Whittaker puts it, Arago submitted the matter to the test of experiment and concluded that light coming from the star behaves in all cases as the reflection and the refraction, precisely as if the star were situated in the place at which it appears to occupy, in consequence of the aberration, and the Earth were at rest. So the apparent refraction of the moving prism is equal to the absolute refraction in a fixed prism. Well, that's no good, because if the moving prism has a 30-kilometer velocity component to it, due to the Earth being in motion, then you're going to have to make a correction to compensate. And he found that you didn't have to. So the implication there is that it is stationary. There's that the Earth is stationary. Otherwise, there's no explanation really, because there's no velocity correction. So then that brings us to Airy's failure. So the first of these was done by Arago, right? And then Airy came along in, what year was that? 1879, I want to say. It's right here, I think. 1872. I was close. Okay, so 1872, Airy comes along. And his hypothesis is that if he has to that a telescope, actually, let me back it up a bit. So James Bradley was observing stars with a telescope in the 1700s. I can't remember the exact year, but it was in the late 1700s. And what he found was that a star at his zenith he had to tilt the telescope forward slightly to keep the star in the center of the telescope. And his hypothesis was, this is the guy that when you plot that deviation over a course of a year, you get stellar aberration of 20 arc seconds. And they're like, oh, that's a ratio of 30 kilometers a second when you plot it against the speed of light. So maybe the Earth is in motion. Maybe that's what produced the angle. Okay. So to settle the matter, because looking through the telescope itself it doesn't tell you anything if we're moving or if the starlight already comes in at an angle and the sky's moving, right? So to settle it again for the second time, Airy was like, okay, if I have my telescope pointed at a star, 90 degrees zenny, when there's nothing in the telescope, it's just air, we can't tell if the Earth is moving or if the stars are moving. If I fill this telescope with water and I have to tilt it further, then that means I'm compensating for Earth's velocity and the starlight isn't already coming in at that angle. And if I don't have to tilt the telescope, that means the Earth is stationary, and the starlight already came in at that angle. So the hypothesis was that based on a fixed ether and the Earth moving through it, that any deviation or any tilt angle measured would be put forward as the velocity of Earth. And for every arc second that they were going to tilt the telescope, that corresponded to 1 kilometer a second. So the prediction was that over the course of a year, divided up into 6 months, they would have to tilt the telescope 6 months by 15 arc seconds total. So every month they're adding another arc second, essentially. And then they would have to bring it back another 15 arc seconds because they're moving away from the stars, right? So to compensate that for the offset. So a total of 30 arc seconds over the course of a year, 15 6 months, and then 15 back over the other 6 months. They measured a difference in 0.8 arc seconds. So not even close to their prediction. That's It's not even tenable to say that, that the outcome of that was that the Earth is in motion. Now, people will say, "Oh, isn't this just a failure to predict the ether?" No, this is a velocity. This is about velocity being detected, right? The stationary ether part was for electromagnetic propagation. That wasn't for the velocity itself, right? All right, so now to move on, we get it to Michelson-Morley, right? So the ultimate test, the ultimate experiment of Michelson-Morley, the ultimate test of Newton's dynamics was Michelson-Morley, right? Through Fresnel drag and what was the other one that they did? I can't quite recall. But they had substantiated that they could measure linear translational motion, that they could measure velocity using light, and then having light at a right angle to itself over a larger distance. The hypothesis was that the light going against the direction, or going perpendicular to the direction of motion, would have a delay because it's being dragged through the ether. It would be slower, right? So the measurement that they got was just over one fringe. They predicted 0.05 of a fringe, but they measured 0.1 of a fringe. Or I'm sorry, 0.01 of a fringe, which gives, what'd they come up with? They came up with like 6 kilometers a second, right? Yeah, 6.5 to 8 kilometers a second. That's what that comes out to. The accuracy of this device was 0.04 of a fringe. So they could measure down to 2.5 kilometers a second and get a definitive reading. Now, they got 0.01 of a fringe, so well within their error of tolerance to detect motion, and they were nowhere close to what they needed. So this dotted line is their predicted amount for the minimum and maximums. And this is what they actually measured, the solid line. So the only way you could interpret this is you have two options. The Earth is stationary with respect to an ether wind, or you could say, right, because this is interferometry, and the principles from Michelson-Morley, the same equation that they use today to derive the Sagnac effect and ring laser gyros and all that, right? So they were dead accurate with this proposal. What they did here in the 1800s is exactly what people are still doing today and how they calculate the fringes and how they count them. So this was dead accurate, right? But they rounded this down to a 0 and said, oh, well, I guess the speed of light can't be used to measure linear motion, et cetera, right? It was very, very, very perplexing for them. So let's see here. Let me make sure I covered everything I wanted to say about Michelson-Morley. I think that was about it. Okay, so we'll move on. So some other analysis have been done in more recent years to show the measurements. So they redefined all of physics over these, 6 days. And then based off of these measurements, they had to redefine all of physics because Newtonian dynamics as applied to the sky had just been catastrophically falsified, right? So you don't see too many people doing analysis on Michelson-Morley or bolstering it or whatever, because to bring it back and acknowledge the measurements as is in the first order is a direct falsification of relativity theory and the Copernican principle that the Earth is in motion, right? So here's some analysis done on those same measurements. And what we see here is that these are statistically significant. They're not zero. They're not. These are positive non-zero measurements, right? So they'll go on to say that the Michelson-Morley apparatus doesn't produce any fringe; it gives a null, right? But then when they have a Michelson-Gale-Pearson apparatus, right, where the light completes a circuit instead of being a right angle to itself, they go, oh, this one, predicts a fringe. This is what we measure. And they call that one the rotational one, et cetera, right? But not the subject of the matter here. But we are going to look at some more Michelson-Morley type measurements. So this one's from Kennedy and Thorndike here. and they were using a asymmetrical Michelson-Morley apparatus, which is why they got such a high velocity. They got 15 plus or minus 4 kilometers a second, and they end up, that's pretty close, right? To what was it, 30 kilometers? They're getting up there, right? Now, they round this all down to 0, guys. They go, nope, this is actually all air, because in view of the relative velocities amounting to thousands of kilometers per second known to exist among nebula, this scarcely can be regarded as one of the other clear null results. It is the same order of precision of the Michelson-Morley experiment. Oh, no way. So you could measure down to 1/10 of a fringe, but actually with the asymmetrical apparatus, it's not as accurate, because that's why they got that huge swing in the deviation. But they would have been of the same 8 kilometers a second as Michelson-Morley, had it been symmetrical. But anyway, so they disregarded experimental evidence, though, based on the assumption of these compounding velocities. They're like, oh, dude, it would be thousands of kilometers a second. This is speed of light must be constant. It's not registering anything, boys. So that's where they were at with that. Not a great way to interpret data. So anyway, we'll take a look at Michelson-Morley was then continued by Dayton Miller, Hector Minera, and Yuri Galev from the 1930s to the late 1990s, early 2000s. So these experiments and measurements and the periodicity of the measurements have been repeated. So I'm not going to get too much into the history of Michelson-Morley or the continuation of those and the specifics of the periodicity and all that, because we're sticking to kinematics and dynamics. But needless to say, the measurements were repeated and do not give a conclusive heliocentric velocity, and it would be more akin to interpret it as either the Earth is moving way slower than they expected, or the Earth is stationary with respect to an ether wind. So now we're going to get into link contraction and time dilation and covariance and invariance. Okay, so the narrative that we're told about invariance is that, that we're told about electromagnetism and Galilean transformations is that relativity theory was the only thing that could restore motion, Galilean transformations, to Maxwell's equations for electromagnetism. So these equations utilize, now we're told that it's described as Lorentz invariance, right? But it's actually Lorentz covariance, because what's happening here is that they're establishing the constancy of C, right? And they're using link contraction and time dilation as the mechanistic change in the coordinate system to provide the constancy of C. So velocity and time are going to be functions of the square of some velocity over C squared. And what that gives you is a really tiny interval, really tiny deviations and whatnot. But the purpose there was that the introduction of time to the coordinate system was the only way to restore Maxwell's equations. And the way that Einstein introduces time is he introduces it through proper time, meaning that it's reference frame dependent, essentially, right? So if you're in the moving frame, you're experiencing proper time relative to some stationary frame that's defined by coordinate time. So there's no simultaneous absolute time. There's only time relative to some other thing, some other stationary reference frame, right? So that's the way that they look at it for that. Now, when you need C to be a constant, you use a Lorentz transformation, which introduces covariance by adjusting the time axis and the length axis, the x-axis, to create invariant transformations of C. So you could take C in the stationary frame, and then you're like, okay, cool, C is measuring C. And then you could apply link contraction and time dilation to the moving frame, and you could go, oh, this person's also going to measure C as well, because in their proper frame of motion, they're contracted and time is dilated by the square of their velocity over C squared. And that will make them see as well. So that leads to the invariant transformation, but in doing that, by adjusting the x-axis and the time axis to compensate, that is called covariance. Okay, so Lorentz invariance is only supplemented by covariance, and then in general relativity, invariance is pretty much dropped altogether, and it's just about the covariance of the transformations, where you get into how is this metric tensor responding to the transformation, right? And the metric tensor being the thing that's describing the coordinate system. So when you get into space-time, you get into g mu nu, where it would be, or g mu nu, where you would have how space-time is bending in relation to the energy or mass that's being conserved into a gravitational field, which we'll get to in a second. Well, all of that is going to provide those relationships, and the changing of that bending and warping to maintain a constancy of c. That's all called covariance, right? Now, invariance is supposed to represent physics and have physical meaning and give physical meaning to these equations when they talk about the invariance of the laws of physics under transformation to different reference frames. That invariance is supposed to establish the physical meaningfulness of what that constant in physics represents. And it's supposed to be the same in whatever frame it's transforming into. It's like, okay, cool. And if the transformation doesn't work, right, then it's non-invariant. But if you introduce covariance, where you can make predictable adjustments to the coordinate system, right, because the x in time contract as a function of the square of the velocity, well, now it's a predictable amount of contraction and dilation. And because it fits that criteria of predictability, that's where they get covariance, right? So they think that so to do the math and link, contract, and time dilate, you're doing covariance to try and assert the invariance of C. So if you need C to be C, you use a Lorentz transformation, you use Lorentz symmetry, which will give you Lorentz covariance. All right, cool. We have our trusty relativistic calculator here, where there's no velocity addition to C. C minus V or C plus V is always going to be equal to C. Right. So to show what that Lorentz contraction and time dilation and proper time and the deviations therein looks like, we have here the time coordinate system and the x coordinate system. So this is the coordinate time, right? These are stationary observers, T and X, stationary observers. Now sometimes they'll talk about time as the world line. So if you ever hear that term, that's what they're talking about. The world line is always perpendicular to the direction of motion. So X is going to be our direction of motion, and the world line, the timeline, is always going to be perpendicular to that. So anyway, now for the moving frame, we have X prime and T prime. That's going to be time in the moving frame. So if you're accelerating, the square of your velocity is going to dilate time in link contract. And that can be represented by the hyperbolic curvature given here, right? So depending on how fast you're moving, you're going to experience more time dilation and link contraction at that hyperbolic rate. So that's why you see these, all these lines make a hyperbola, right? So that's why that looks the way it does. All right, so we'll move on now. So we already touched on Einstein's field equations for general relativity and covariance in that regard, right? So you take the system, you take whatever your, the mass of whatever, blah, 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 right? That's going to be conserved into a gravitational field that's going to be distributed by 8 pi g over c to the fourth, which is just like the way I like to look at it is it's like the gravitational, like you could think of the gravitational field as like a density gradient. So this is the distribution of how much gravity can be distributed per cubic centimeter, over an area as you get further away from the source, right? So that's the way I look at that ratio for that. And then that ratio is actually going to determine the curvature of space-time. So these over here, g mu nu and little g mu nu, and the lambdas for cold dark matter. So you can just set that to 0. But anyway, these describe space-time curvature in relation to the mass and energy that's being conserved. And so this will the curvature will keep the speed of light the same. and the coordinate system itself will bend in relation to the conservation of mass, energy, and momentum. So this is covariance, right? This is straight up covariance. All right. So well, we already covered covariant, invariant. We did all that. So we're looking pretty good. So I just wanted to show you guys the significance between invariance and covariance here. So I went over Lorentz and how Einstein restored, Maxwell's equations and motions and all that by using two arbitrary time coordinates, right? Well, what Hertz found before he died, and what was continued on and researched by Thomas Phipps, he found that when you take Maxwell's equations and you add, what did he do? Oh yeah. Okay. So you add absolute time to them, and then for the time for the moving frame, you take a derivative of absolute time, and that applies to the moving frame. So the way that Einstein did it was that stationary time was just arbitrary, and the proper time, right, was the one in the moving frame. So on the inverse of that, if you say, hey, no, there's an absolute time, there's an absolute space, there's an ether, etc., right? You can apply, or you can set up absolute time for the stationary frame, and then you could take a derivative of that for the time in the moving frame, and boom, you're good to go. But when you do that, you get left over with this velocity component. And Hertz didn't know what to make of that velocity component, and then he died before he could, fully flesh it out. But his thoughts on it was he was that was an ether wind, like in reference to the, like, mechanistically, like how I would frame it. If you were to say, like, Michelson, Gale, Pearson, ring laser gyroscopes, where are they detecting ether wind as a physical mechanism? This is not the same kind of ether wind as the physical mechanism. This would be, when he says ether velocity for it, he's talking about the velocity of the detector. So when you take that velocity component and put it into the moving frame, well, suddenly you have actually restored Galilean transformations to electromagnetism without contracting space and time. So this doesn't lead to symmetrical space-time transformations. This actually breaks space-time symmetry, right? Because we're not adjusting X in time. The math is a little more rigorous to do, but it does give you actual physically invariant transformations, not something that's based off of covariance where, time's not absolute, your apparatus contracted, all that kind of stuff. None of that's required here. So this is just kind of breaking down all of that in relation to Maxwell's equations. So he shows the transformations. I was going to put all that in the prez, but, like, honestly, like, I know nobody cares about that. They can look for it there. They can look at it if they really want to. But anyway, he's just laying all that out, sets the parameters for free space, and then shows the transformations for it. So all these equations that describe the current, density, the strength of the electric field and the magnetic field and the relationship and all that over time, all of that is restored using the Hertzian transformation with the velocity component and adding absolute time and taking the moving time as a derivative of the absolute time. Now, to end off the end to 48 minutes. God dang, this turned out to be a long one. So to end the presentation, to round it all out, we have, comments on taking pictures of the sun and doing spectroscopy, right? What is solar spectroscopy anyways, right? So the entire model of the sun and it being, nuclear fusion or fission and all that, and the gas, and it's reaching, thermal equilibrium and all that stuff. Well, all of that is based on hydrite being in the spectroscopic readings. And if that element isn't found, then the whole idea of the sun having this amount of mass and based off of this type of material to produce these elements so that it's this heavy, so that when it gets this hot, it turns into this element. Well, this hydrite has to be present in the spectroscopic readings, and it's never been observed. The whole entire model depends on that. Because what happened was, when spectroscopy came about, they found, they started studying emission lines in the lab, and they were like, oh, snap. We could figure out what these materials were made of based off of the spectroscopic readings they give based off of these emission lines. Okay. So what they did when they looked at the sky, they saw continuous emission lines, and they were like, oh, that's different from what we see in the lab. What do we do? Even though the colors are the same and they represent the same patterns of what we would look at in the lab, but this continuous spectrum, just like, what do we do here? So you have to make some assumptions and some assertions. You have to introduce some coefficients. You have to get into all of that to interpret these continuous spectrums as the same, or being possible as being created from, this giant gas giant in the sky, right? A lot of presuppositions and math goes into reinterpreting that as what they see in the lab. And it all hinges on hydrite, right? So they've never found it. This is from 2010, the Astrophysical Journal. Although the detection of hydrite in astrophysical environments remains elusive, Ross and others from 2008, a firm acceptance of its presence is that it exists. Okay. Well, if it doesn't exist, then the whole conceptualization of a gas giant and nuclear fusion and all that, it goes right out the window. So of course there's a firm acceptance of it, even though it's never been measured. It's mandatory, right? So when we get into Ross's paper here, they say that they can't find it. Oopsies, and then they start going into like, well, actually, I don't think we'll be able to find it near the sun. Maybe we'll be able to find it in interstellar medium. What's interstellar medium, you ask? Whatever is between the distance of stars, right? When they look at a galaxy and they're like, what's these two stars here? The distance between them, that's interstellar medium, and there's probably gas in there. And when we look at that, that's where we're going to find the hydrite. They've never found any hydrite in there either. So we'll read the end here of their paper. At this time, there are no plans for the UV spectroscopic beyond the Hubble telescope's cosmic origin spectrograph, which will have limited to no sensitivity to the wavelength region of the Fresh-Bach resonance that are expected. So a further sensitive search for astrophysical hydrite may be a long time coming. Well, we all know how long it took to get Hubble off the ground. I think that was like a 20-year endeavor. What was it, like $50 billion over budget or something crazy? But yeah, they explain here that, well, we need more sensitive equipment to detect it, and we're never going to find it. Oops, that's crazy, dude. But everything hinges on that, and you can learn more about that from the Sky Scholar video. I'll pull that up real quick. Actually, I'll include it in the description. But anyway, Sky Scholar's got an awesome video on it, breaking this down. If you go to his channel and type in, I'm just going to do it now, doing it live. Sky Scholar. If you go to Sky Scholar's channel and search Dave, he did a response video to Professor Dave, who tried to argue against this hydrite. Yo, real quick, to all the little homies at home that are going to start hydrating and repeating Professor Dave, mandatory, before you get a response from me, you have to watch this video and have it explained to you about why Professor Dave is wrong, right? Because this hydrite isn't the same hydrite that's in a lab that's readily available and blah, 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 right? Not the same argument. Dude, Robitaille systematically destroys all of that. So anyway, if you think the sun is a gas giant that's experiencing nuclear fusion and experiencing thermodynamic equilibrium and all that, definitely watch this video, and then we could discuss the hydrite situation or lack thereof. But until then, don't care. All right. So I think that's everything that I wanted to cover. So to kind of reiterate here, we started with which its position was that there's no dynamics involved, and you can derive downward acceleration kinematically. And that's exactly what Daryl showed him 3 times, but didn't understand the significance of it. And then, so he continued to argue as if he had made a substantial point, because, he did do the math, right? Like he did do the math, but unfortunately it didn't make his point, which is which is what Whitsett's point was. So hopefully that helps clear up kinematics and dynamics. If you have any further questions, I have a kinematics and dynamics playlist that can be viewed on my channel, which will be included in the description as well. Let's see, playlist. And kinematics and dynamics. Awesome.
Kinematics is an important.
All right. Awesome. So hit this up, learn this, because the distinctions in the and what happened here, right, is a product of indoctrinate. Like, and I don't want to say anything bad about there. Like, I don't care, right? But educationally, mainstream is combining covariance and invariance, and they're blurring the distinction between kinematics and dynamics, right? And as a result of that, you will get a situation where you think what you're doing is dynamics, but it's kinematics. And it's pretty straightforward. Just take an objective look at it and you'll be like, oh, okay, got it. But there you go. Hopefully this helps.